Today's tricky topic in 2 minutes is Lenz's law. Lenz's law has to do with a magnetic effect, and well, it's one of the coolest things I think you'll see. So this is a pretty strong little magnet that I got here. I'll put it on my chair. Click. Kind of loud, right? A little hard to pull it off. So it really sticks well. It's neodymium, so it's a pretty strong magnet. So I got a copper pipe here. Magnet doesn't stick to the copper. In fact, in a most subtle way, copper is actually repelled a little bit from permanent magnets. It's something called diamagnetic. So there's definitely no attraction going on here. Even in the strictest sense, there's a little bit of repulsion going on. Okay, so this fits about, it's a little bit smaller than this, right? Fits in there, but there's no really, tightness to it. There's a little bit of room in there. So what you're going to see is this thing fall down the pipe, and you're going to see how long it takes to get down the pipe. Now, if it was normal, of course, this is only a couple feet long. It wouldn't take long for it to fall at all, right? But watch, this is not slowed down. This is real time. There you go, right? So it obviously takes a really long time for this magnet to fall down the tube. So the question is, what's going on if this is not really attracted to it, but it is really attracted to steel? So when a magnet falls down through this copper pipe, there's a magnetic field associated with it. And when it crosses over the copper, when it passes by it, it's a magnet moving past a conductor. And anytime a magnet moves past a conductor, you create an electric current inside the conductor. This is really how all generators work, electric generators work, by moving magnets relative to conductors. So what this is really doing is this falls down the pipe here, is it's creating little electric currents in the copper pipe all the way as it falls down there until it comes out the bottom. So when you make electric currents within that copper, they in turn create a magnetic field themselves. This is a right-hand rule, and if the currents, let's say they go around this way, I point my right thumb in the direction of that current, and then my fingers would curl up to create a magnetic field where the North Pole would be up. And the opposite would be true as if the currents were going the other way. But the bottom line of it is this: if the magnet is falling down through this tube, it's creating a current within the tube as it falls, and that current in turn creates magnetism that opposes what created it. So Lenz's law, bottom line is, anytime you create an electric current within a copper conductor or any other kind of conductor, that current is going to create a magnetic field that opposes the magnetism that created it. In other words, it's going to try to slow the magnet down every chance it gets.